Okay, so we've discussed the data. We have n d-dimensional vectors, that's the data. We've discussed block 2, which is the model that we're going to define, a multivariate Gaussian with an IID assumption. We now move to block 3, which says, how do we learn the parameters of this model? Again, we've said that the data is IID Gaussian with a mean, and that Gaussian has a mean and a covariance, but we don't know what the mean and the covariance are yet. And we also don't know how do we pick a good value of the mean and covariance. What is a good value? What's a bad value? We haven't even defined what's called an objective function to optimize. So this all pertains to block 3, the inference or the learning portion of the flowchart. So with this block, we have to define an objective function. We have to say, here's a mathematical function, and it always boils down to defining some mathematical function, which is a function of our data and a function of unknown model parameters that are defined by block 2 for us. And this math function tells us which values of those parameters are good, which are bad. If we have 2 values of the parameters, and we evaluate that function at those 2 values, then the value that is larger or smaller, depending on how we define our objective function, but that evaluation will tell us which of the 2 values is better than the other value. So we need to define an objective function. Then once we've defined that objective function, we need to come up with some sort of an algorithm for then optimizing it, finding the parameters that maximize or minimize the function, depending on which of those 2 we want to do. So a common approach with probabilistic models is something called maximum likelihood estimation. And so we'll look at that for the remainder of this lecture. So with the maximum likelihood approach, we simply want to find the value of theta that maximizes the joint likelihood function. So we've defined a model. This is a probability distribution on our data. For a particular value of theta, it tells us what is the likelihood of the data coming from that model. What is the probability of the observations that we have given that particular value of theta? And maximum likelihood simply says, well, if we've defined a model and each evaluation of this function for a particular theta says how likely the data is given that value, we simply want to find the value of theta that maximizes the likelihood. We want to find a value for theta that makes it the most, that says that this data set is the most probable from a multivariate Gaussian having this parameterization. So in a sense, we're fitting the data that we have the best. And so that defines the maximum likelihood problem. We want to find the argmax over theta, so we don't necessarily care what the value is. So we aren't doing max theta, we're doing the argmax, meaning we care what the value of theta is more than what this function evaluates to at that theta. So we take the argmax of theta of the joint likelihood, and we call that the maximum likelihood estimate. Now for this maximum likelihood estimate, we need a way to find the maximum values. So we can simply take arbitrary values of theta and plug them in and continue to do that until we're satisfied that we've picked the best one out of the options we've given ourselves. Or we could do a more principled approach where we actually define some sort of an algorithm that's going to find for us very efficiently the optimal solution. And so that leads to the maximum likelihood equation. So we have this joint likelihood function. We've made an IID assumption, so we can write this thing as a product of the likelihoods of each individual observation. This now gives us some function that we want to maximize. And so to do that, we follow the maximum likelihood criterion, the optimality criterion, that says that the maximum of a function is the point at which the gradient is equal to 0. So if we want to think about this in terms of an image, we have something that looks like this. This is a very rough thing. Now we evaluate this function at all values for theta. We want to find the maximum. That's going to be the point here at which the gradient is equal to 0. So we can't move in any direction and improve our function. We can't modify theta in any way to improve the value of the function. So we find a peak. So this is what we want to optimize. We want to find the point of theta such that the gradient of our objective function, in this case the joint likelihood, is equal to 0. So we have more that we can do with block 3 here. We've defined the objective function. This is a quote-unquote block 3 problem. This is defining the thing that we want to optimize, the joint likelihood. We've said how we can do that. We can find the point for theta such that the gradient of the objective function is equal to 0. But we're not yet done. We have to give some sort of an algorithm, something we can run on a computer that will do this for us. So this will require a technique that is problem specific. For this particular problem, we'll discuss one algorithm. For other lectures, we'll define models for which this particular algorithm has no use whatsoever, in which case we'll define another algorithm for that particular problem. So here we're working with probability distributions in an IID setting. And more often than not, this leads to something called the logarithm trick that makes optimization very, very easy. So in this case, if we want to take the gradient of the product of likelihoods, this product is, again, because of IID assumption. If we want to take the gradient of this, actually calculate derivatives with respect to theta, and set to 0, we very often will find that this is a very complicated thing to do. It's not a nice thing to work with. And that's because we're taking a derivative of a product of many things. So here we're going to use the fact that the logarithm is a monotonically increasing function in R+. What this means is that if we evaluate the logarithm of a positive number, then if that positive number is increasing, then the logarithm of those numbers are also increasing. So simply put, the logarithm doesn't change locations of maximum and minimum. In this case, we can take a joint likelihood that can be written in this way as a function, as a product of terms. And when we take the logarithm of that product, we have the fact that that turns into the sum of the logarithm of each individual term. So the logarithm of a product of functions fi is equal to the sum of the logarithm of those functions. And so this turns our problem into something very simple. And again, we care about the location. We care about the value for theta that maximizes this function. What this means is that even though the maximum of the log of a function g over y is not equal to the maximum over y of the function g, if we actually plug in the value y that maximizes this left-hand side and then plug in the value y that maximizes this right-hand side, those values are not going to be equal. The maximum are not going to be equal to the same thing because the left side is the logarithm of the right side. The argmax is the same, so the location doesn't change. So the value of y that maximizes the log of a function g is equal to the value of y that maximizes the function g, if g is a positive function. So the location of the maximum doesn't change, even though the value of the maximum clearly does change because g is not equal to log g. And since we only care about the location of the maximum, because that's going to be the parameter, we can use this fact that the log of our joint likelihood is equal the maximum of the log of the joint likelihood, that location is equal to the location that maximizes the joint likelihood. Okay, so we're still have to follow through and calculate all of these things. So again, tying it all together, using maximum likelihood with the logarithm trick, we have that the value of theta that maximizes the likelihood, this is the argmax over theta of the product of these individual likelihoods over each data point this is the IID assumption here, is equal to the value of theta that maximizes the log of that product of likelihoods. And the log of a product is equal to the sum of the logs. And so the value of theta that maximizes the sum of the log of each individual likelihood of each point given a parameter theta is equal to the value of theta that maximizes the original joint likelihood. So instead of working with this function, we work with this function. We solve for the maximum likelihood solution, meaning we now have to find the value of theta such that the gradient of this function at that value is equal to 0. And so notice what we've done here. Instead of having to take the gradient of this product, which can be a nasty mathematical thing to do, we now have to take the gradient of the log of each individual likelihood over each data point and sum those all together. And that's going to be something that's very easy to do usually. And now find that the point of theta at which this sum is equal to 0. Okay, so now depending on the choice of the model, there are going to be different ways in which we can actually solve this. So the nicest case is when we can do this analytically. What this means is that we take the log of the likelihoods, we take the gradient, we actually calculate this thing, try to set it to 0, and realize that we have a very simple mathematical equation that we can plug things into to solve for theta. So that's how it's going to work out in this particular case that we're talking about, because it's a fairly simple model. However, for more complicated models, we can't do this. We can't take the derivative and set it equal to 0 and then solve for the value of theta at which that equality holds. So we have to do something with a numerical algorithm. We have to use an iterative algorithm such that even though we can't find the value of theta that maximizes or in some cases minimizes our objective function, we can have iterations where we're continually modifying the value of theta, and each modification is getting us closer and closer to the solution, and it'll finally converge to the solution. So these involve numerical algorithms. We'll discuss several of these in this class. Also, we might find ourselves in the situation where we can't optimize this function exactly. We can only approximately optimize it. And so intuitively, we can think of it in this way. Really, these approximate algorithms are all based on numerical algorithms from part 2. So really, 3 is not introducing any new modeling techniques per se, but it's understanding what exactly these numerical algorithms defined by 2 are going to converge to. So if we have a simple objective like this with one maximum, one local maximum, the global maximum is the local maximum, they're all the same, we can say that we're converging to the optimal point. But if we have an objective function that looks something like this, then depending on where we start, we might converge to a different local optimal solution. So for example, if we have these two local optimal solutions, think of them as peaks of a hill, then if we start in one location, for example, in this location, our algorithm might eventually converge to this point here, which corresponds to the global optimal solution. However, if we start from a different point, like this point here, we can only converge to this local optimal solution, which is not the global optimal solution. So this is going to be something that happens a lot, where our algorithms are only going to converge to a locally optimal solution, and the model space is going to be much more complicated than a one-dimensional space. So we can't inspect it with our eyes to see whether it's locally or how good of a local optimal solution it is, or if in fact it's the global optimal solution. All we can say is that we've approximately optimized our objective function.